going to get started. Before I introduce our guest speaker, I just have a couple of items from the board they wanted me to ask you about. How did you find out about this meeting? Let's show of hands from the website. From the website, okay. The activity schedule. It's in the library, an activity schedule. How about an email? Email. Okay. And how about Facebook?
I didn't know you had Facebook.
Right.
Really?
Oh, yeah.
Oh, okay.
Right.
Cool.
Okay. And also want to remind you, our treasurer is here. If anyone would like to sign up to be a member, our treasurer, Dave Hartzik, raising his hand in the back there. And we have a lot of refreshments and a lot of different types of beverages. We have water, we have some soda, and that's free coffee in Akron. And on that table there is a box, a white box, that's our recycle box. So any plastic bottles or anything plastic or aluminum or even paper, just put in there. We'll sort it out later and clean it up and get it to the right place. So, well, welcome to our May Astronomy Club of Akron public lecture meeting. I'm very happy to introduce our guest speaker, Jeff Woytach. Jeff has been out several times with us, giving different talks, and it's always a very exciting talk. Jeff's worked for NASA for 40 years, and probably just about every type of space exploration project there is. And today he's going to talk to us about the James Webb telescope. And give us an update on what's happening with James Webb. So let's have a nice hand for Jeff.
Thank you, Webb. I appreciate it. Good afternoon, everyone. Thanks for coming out today. We're here to give you something, the universe, thanks to the Webb Space Telescope. I'm going to focus on some of the engineering behind the telescope. Some of the things it's been able to do, some of the things hopefully it's going to be able to continue to do. As we were discussing earlier, the telescope has been in operation now for 5 years. That's how long operations were funded. I have yet to hear if NASA is going to continue funding the Webb Space Telescope. Keep your fingers crossed. Now, of course, orbital telescopes, space telescopes, NASA has been doing for a number of years. This started with the orbiting astronomical observatories. OA-01 was lost in a launch vehicle failure. OA-02 was December 68 through 73. It discovered the halos of gas that surround comets and observations of novas, which found their ultraviolet brightness increasing with their decline in optical brightness. OA-03 was called Copernicus, was launched in 72, carried an X-ray detector built by University College of London's Space Science Laboratory and a UV telescope built by Princeton under the direct supervision of Lyman Spitzer at the time. It operated until February 1981. And of course, I think everyone is familiar with the 4 great observatories that covered a wide swath of the electromagnetic spectrum. Compton Gamma Ray Observatory, Spitzer, which covered infrared, Chandra, X-rays, and the Hubble Space Telescope, visible light and ultraviolet, a little bit of infrared as well. Of course, the only one of these 4 that is still operational is Hubble, and it is nearing the end of its life because of its reaction control wheel failures. I wanted to put together a summary, very quick one, of what discoveries have been made by Webb. I couldn't, because it would have been an entire presentation by itself of single lines. But these are just some of the things. It's identified some of the oldest known galaxies as they were over 13.4 billion years ago, when we believed the universe was only a fraction of the size it is now. And I'm going to put a caveat in there, and we'll talk about it. The observable universe was the smaller size than it is now. It's discovered mature galaxies in the early universe that seem to have formed faster within hundreds of millions of years after the Big Bang than our cosmological theories suggest. It's analyzed some of the earliest black holes and their host galaxies that evolved 500 million years after the Big Bang. Its spectroscopy instruments have looked at exoplanets and have detected molecules like methane, carbon dioxide, sulfides, which hint at life and liquid water oceans. A different type of planets that are somewhere between a planet and a star. So a whole new class of planets. Plus hundreds of rogue planets. Planets drifting through the universe without orbiting a star. It can JWIST, because it focuses on the infrared part of the electromagnetic spectrum, can pierce dust clouds. So it has found a lot of stars being born. Hubble has identified those. JWIST has identified even more. It's found areas outside the Milky Way, clouds of interstellar gas and dust that have organic molecules and alcohols, the basic building blocks for life. So they're not that particularly unique in the universe. And it's helped map carbon dioxide on Jupiter's moon Europa, which is proving evidence of that the key ingredients for life originate from the liquid ocean that is underneath the 20 miles of ice that cover Europa. It's mapped seasonal storms on Uranus and done extensive mapping of the Uranian rings as well. If anyone has questions as we're going along, please feel free to raise your hand. We'll also do questions at the end as well. The telescope is named after NASA's second administrator, James Webb. He was a director of the Bureau of Budget, now which we know today as the Office of Management and Budget. He was also a U.S. Undersecretary of State. He executed Kennedy's goal of landing a man on the moon and returning him safely to the Earth by the end of the decade. He actually resigned as NASA administrator before Apollo 11 touched down. He had a very key role in creating the Manned Spacecraft Center, which is now the Johnson Space Center in Houston. And of course, the political pressures on him were to focus on Apollo. We've got to get astronauts on the moon ahead of the Russians. But he realized that NASA was more than that. It needed planetary exploration, it needed science. He ran, approved and funded the Mariner and Pioneer space programs, and those space telescopes that I talked about, the OAOs, were funded and developed under Webb. He was a proponent of diversity programs in NASA, and because of him, NASA publicly supported the Civil Rights Act in 1964. And on occasion, he and Wernher von Braun confronted and lectured Alabama Governor George Wallace about segregation right in front of the press. By the time he left NASA, it was considered a model agency for other government agencies. There was a move at one point to rename the telescope because of the times that Webb was part of. Segregation was the accepted norm. And he was being blamed for following the accepted norms. But the history record shows otherwise. Astronomers and astrophysicists are, to me, superheroes, because you all have an enormous superpower. You're able to look backwards in time. Because right now, obviously there's no astronomer, no astrophysicist, no cosmologist, not even Neil deGrasse Tyson, can tell me what the universe looks like. It is impossible for us to know what the universe looks like. We know what the universe looked like, because as we look out into space, we're looking backwards in time. Webb telescope is taking that superpower and amplifying it with another power. That's spectroscopy, particularly in the infrared areas of the spectrum, to help answer fundamental questions about the universe. The goals of Webb are to search for the first galaxies formed after the Big Bang, determine how they evolved, look at star formation from its initial beginnings to the formation of planetary systems, and measure chemical properties of planetary systems, including our solar system, using spectroscopy. Its instruments are near-infrared, mid-infrared, and even some far-infrared instruments. Its engineering innovations are astounding. The lightweight optics, a deployable sun shield, the most complex deployment that has ever been undertaken in space. The folding segmented mirror, we're going to talk about. The improved detectors, cryogenic actuators, and mirror control and shutters to control the temperature of the spacecraft. Now, of course, we're all constrained by the electromagnetic spectrum. We have no idea what an object looks like. We have absolutely no idea. Because what we see, what we perceive, is a very narrow band of electromagnetic radiation, either reflected by an object or absorbed by that object. So we're seeing an image. We are not seeing the object. And the electromagnetic spectrum covers extremely low frequency waves that are the size of a building, all the way up to frequencies of 10 to the 24th hertz, with wavelengths of 10 to the minus 14th meters. That's a 1 with 14 zeros in front of it. That's gamma rays. So that's going from radio waves to microwaves, like your microwave oven. You're cooking with a radio. It's at a frequency level that water molecules really like. And when they absorb that frequency, the oxygen, the bonds that the hydrogen has with the oxygen vibrate. That releases heat. That's what cooks your food. You're cooking with a radio. And then you come up to us poor puny humans who can see that tiny little band from the red up to the violet. That's all we can perceive directly of the universe. Ultraviolet, we can feel, of course, we get a sunburn. We can feel infrared, we call it heat. But X-rays we cannot perceive, gamma rays we cannot perceive. They can kill us because that's ionizing radiation to us. That's deadly to organic molecules. But that's all electromagnetic spectrum, and that is what the universe is. Sir Isaac Newton, since he was bored, he had nothing to do, locked up in his estate during the plague. You know, no PC, no Game Boy, thank heavens. Did experiments with a prism and showed that white light is composed of light of different colors. By passing it through the prism, each of those different colors equates to a different frequency, a different wavelength, and they are refracted differently by that prism. So what comes out of white light goes into a prism, what comes out is a band of colors. Well, skeptics argued that no, the prism was adding the colors to the light. So he debunked that very simply by taking another prism, turning it around, passing the colors back through it, recombining them back into white light. That's spectroscopy. Breaking down light into its constituent colors. And that's what the observatories do. Hubble is looking at ultraviolet, infrared. It's up at the high end of that visible light spectrum of what our eyes can perceive. Spitzer was way down at the infrared side. It was looking at heat. Webb's right in the middle. There's a little bit of overlap in the ultraviolet, mostly the near and mid-infrared, and a little bit in that far infrared. So when you put the three together, you're able to get a much better idea of the observable universe. Yes, sir?
Are there any telescopes that focus on the gray bands?
When you start getting down into the microwave and a radio, that's radio astronomy. When you get up at the higher end, X-ray was Chandra Observatory, and the gamma ray, Compton Gamma Ray Observatory, looking at gamma ray bursts across the universe, was that data as well. So yeah, thanks to those, we've covered a lot of this waterfront, but there are still gaps, and there isn't quite enough overlap. And since you asked a question, if you ask a good question, you're getting a J-List mirror segment. Not full size, you know. So spectroscopy tells us about the composition of materials. Some materials, some atoms in the periodic table will absorb light. Others will take that radiation and emit light. And by looking at where those bands are, we know what material is present. That's what spectroscopy lets us do. But the universe is moving. It's expanding. So you have the Doppler effect. If a star is moving away from us, the light that it's emitting is getting stretched out because it's moved away. It's shifting toward that red end of the spectrum. If it's moving toward us, it's catching up to its own light. So they're compressed. That's going to the blue end of the spectrum. You hear the same thing if you're in an ambulance coming by and it's coming toward you and going away from you. You hear the pitch come up and then you hear the pitch go down. Same thing. The Doppler effect. Exactly. Named after Christian Doppler. The picture on the right, my wife and I were in Austria in December of 24 doing Christmas markets. That's the birthplace of Christian Doppler in Salzburg, Austria. The building behind it, to the left, is the birthplace of Mozart. Talk about, that's what I call a neighborhood. This is Edwin Hubble, whose observations in 1920 led to the conclusion that everything in the universe is expanding. There's still argument about how fast, the Hubble tension, as it's called. Jay Wist seems to be confirming Hubble's original observations, but there are still other calculations that say otherwise. Our science is by no means exact. But the faster and further away an object is, the more those spectra and those frequencies are stretched out toward the red. So those absorption bands for various materials, we can still look for them, but we got to shift them to the right, to the red end of the band. Depending on how close it is, or how far away it is, how fast it's moving, will show those same bands, absorption or emittance bands, in those at the red end of the spectrum. We just have to look at the size of the bands, the placing of the bands, and we can still tell what the element is that's responsible for the spectroscopic lines. We time travel all the time. I can think of a different way to phrase that. We time travel all the time.
What do you say?
We're constrained to the speed of light, about 186,280 miles per second. When we look at the moon, we're seeing how it looked about 1.3 seconds in the past, because that's how long it took reflected light to reach us from the moon. When we go outside and look at Sol, we're seeing how it looked at almost 8.5 minutes in the past. If the sun were to extinguish right now, we'd still be in full sunlight for almost 8.5 minutes, because that's how long it took light to reach us. So you're seeing how the sun looked. Take your solar telescopes out, look at the sunspots. You're seeing how they looked 8 minutes ago. Pluto, edge of the solar system, almost 7 light hours away. So think about it. When we send a spacecraft out to Pluto, we can't target where it is because it's not there. We see it there, but it isn't there. We have to target where it is, not where we see it. Except on Tuesday when it's dark. Proxima Centauri, closest star to Sol. We're seeing how it looked 4.3 years in the past. Our galaxy, the Milky Way, we're out in the suburbs. We're almost 30,000 light years from the center of our galaxy. So we see the center of our galaxy, how it looked 30,000 years ago, because that's how long it took light to reach us. The nearest spiral galaxy to us, Andromeda, 2.5 million light years.
Whoa.
We're seeing it before much of what we consider life today even existed on this planet. And the edge of the observable universe is estimated at 13.7 billion light years. So what that means is, in our theories, the universe began with something called the Big Bang. And that doesn't mean that everything in the universe was concentrated. It means that the universe did not exist. It was in a single point. And that point somehow began an expansion. It cooled, and after about 400 million years or so, the first stars began to form from hydrogen that was spread across the universe. Some were closer to other. Gravity took over, started pulling things together, the first stars formed. There was only hydrogen. in the original universe. All the elements of the periodic table were made by the fusion process in those early stars. They exploded, they threw that material out into space. That material coalesced in other nebula, which formed the next generation of stars. Those lived out their lives, they exploded. I've always said, to me, the most valuable thing about a diamond, there's no difference between a diamond and a lump of coal. They're the exact same thing.
It's just organized neatly.
Exactly. It's in a crystal lattice, under high pressure and temperatures. Because all the diamonds on Earth were once inside a star that blew up. That's the value of a star. Yes, sir. I'm sorry, yes, ma'am.
Are you saying that the first stars formed before there was helium in the
Yes.
universe?
Yes. The only element that existed was hydrogen.
The hydrogen fused into helium
That's right.
and so on and so forth.
Our sun fuses hydrogen into helium at the rate of about 7 million tons per second. And even at that rate, it will exist for about another 4 billion years. There's a huge amount of matter in the sun. And our sun is puny compared to so many stars. Yeah, Betelgeuse, Bellatrix, Rigel, Sirius. Our star is less than 1 million miles in diameter. It's small, you know. That's why, you know, we can.
So, before you proceed,
Yes.
why is that like black to the left there called truncated?
That was before material, the hydrogen clouds and everything started coming together to form stars. There was no light. The universe was completely dark.
Okay.
And that was probably about 380 million years that happened. By current cosmological thinking. Of course, Webb is teaching us that our cosmological thinking isn't necessarily correct.
We gotta rethink again.
As I said earlier, it's what we're learning is teaching us that we got a lot to learn. Looking back to the beginning of the universe from ground-based observatories, we go back about 6 billion years. Hubble, its first deep field. That can't be right. Another one, I'm sorry. This is from the Big Bang. So 6 billion years out from the Big Bang. Hubble deep field about 1.5 billion years. The ultra deep field about 800 million. The Hubble ultra deep field in infrared about 480 million. But Webb is going to take us in those first 200 million years. When there should be no galaxies. There should be nothing. But they're there. So we know our models are not correct. This is one of the early images. This is the pillars of creation in the Eagle Nebula 7,000 light years away. So again, we're seeing how it looked 7,000 years in the past. It may not even exist anymore right now, but we're still seeing it. It's about 5 light years across. You see a Hubble image on the left, and you see the Webb image with that mid-infrared, able to pierce those dust clouds and see galaxies behind it and the stars within it. Stars that are being born, because this is a stellar nursery.
What's the definition of a nebula?
A nebula is a cloud of gas and dust left over from other stars that have lived their lives and exploded, thrown that material out into space. The sun, our sun, soul, and the solar system formed from such a nebula. There were areas where the concentration, the density was a little bit higher than other areas, and that means the gravity was higher, and things started pulling in, and started pulling in other stuff, and started pulling in more and more, until the sun formed and the planets formed. We see that happening throughout our galaxy and other galaxies as well. The Goddard Space Flight Center in Greenbelt, Maryland manages the Webb project, has established the Space Telescope Science Institute as part of Johns Hopkins University to operate it. It was an international partnership that included the European Space Agency, the Canadian Space Agency. The telescope itself was assembled, tested by Northrop Grumman, which was the industry lead for the Webb project. Some of the different parts here, and then we'll talk about the spacecraft bus is all the housekeeping functions, communications, attitude control, everything to make sure everything is operating as it's supposed to. Big deployable sun shield, because operating in the infrared, it's detecting heat. Well, the sun puts out a lot of heat, so you got to shield it from the sun. And some of those instruments have to be kept even colder, as cold as 38 degrees above absolute zero. And that's done with liquid helium cryo coolers. That's the limiting factor for the telescope, is the storage of liquid helium. It's a big puppy. It's about the size of a tennis court, 46.5 feet across by almost 70 feet long across that heat, sun shield. The mirror is segmented. The Hubble mirror was about 2 meters. The JWIST primary mirror is 6.5 meters in diameter. That's almost 22 feet. You could not build it in one piece like you did Hubble because it would be too heavy to launch, let alone get it where it's located, which is at the Earth-Sun Lagrange point 2. You have the Sun, you have the Earth, and then Hubble is about JWIST is about 1.5 million kilometers from Earth, with Earth between it and the Sun. And that sun shield faces the Sun.
So does that mean that the sun doesn't actually shine on James Webb at all because
Correct.
the Earth is in Earth's shadow?
Correct. Well, it's not always in Earth's shadow, but that sun shield keeps the telescope is in constant darkness. Yeah. Here's that Hubble image of the Eagle Nebula from 2014. And then one of the first images that it did in infrared in 2014 was able to penetrate those dust clouds. This is from Hubble. And then JWIST came along. And this is near infrared from JWIST. And then you have the one I love. I love this one. This is the mid-infrared view of the pillars of creation. I call this the home of the Dementors. But if you look at the tips of those clouds, you'll see glowing red at the very tips. Those are solar systems larger than ours. Those are stars being born. As I said, the telescope mirror itself is almost 22 feet across. If you took Hubble's telescope, try to make it the size Webb needed, you wouldn't have been able to launch it. And as such, we needed a light material, a strong material, because this sucker had to be folded to fit in the launch vehicle fairing. So the mirror segments were made from beryllium. Each segment only weighs about 46 pounds of that mirror, and there are 18 segments in the mirror. It was built on a folding frame, again, so it could fit in the launch vehicle fairing. Each hexagon is a little over 4 feet in diameter, flat to flat. And when you put those together, it allows for a roughly circular parabolic shape. And each section fits together without gaps. The gap has to be no thicker than that of a human hair. Each mirror segment has actuators on the back of it, so it can bend that mirror to allow it to focus. And then there's also a center actuator to fine-tune that focus. Again, it can move it to about 1/10,000th the thickness of a human hair. That's how fine the actuators are. But the mirror is set up as you see here, so it's essentially mimicking 3 concentric circles. The inner, the mid, and the outer. So it's like having 3 parabolic mirrors together. Making the mirrors was a trip and a project unto itself. They had to make 14 stops to 11 places across the US for manufacturing. Beryllium is very strong. It holds its shape across a great range of temperatures. It conducts electricity and heat, but it's not magnetic. The beryllium was mined in Utah and was purified actually here in Ohio. It was placed into a stainless steel canister and pressed into a flat blank. That resulting chunk of beryllium was then cut in half to make 2 mirror blanks. And they were shaped in California by cutting away most of the backside of that blank, leaving ribs that are only about 1 millimeter thick. It still leaves the strength there, but it takes away a lot of the mass.
Is it the same material as on Hubble, or is it a different?
The mirror?
Yeah.
No, mirror, Hubble's is not beryllium. I forget what the backdrop is. But the Hubble mirror is like an Earth-based telescope mirror.
Oh, like just a regular
Yes.
refractor?
Yes, yeah. Because it's an offset Schmidt-Cassegrain, isn't it, Hubble?
That sounds correct, yes.
I think, yeah. It's been a long time, so I kind of take that with a grain of salt.
Only one that can stand space cold.
Cassegrain, there's no corrective plate on
That's right. You're right. Okay.
this. And I thought the new was some type of.
Yeah, it is. It is. It's glass. Yeah. Actually, the segments here on Webb actually have a very thin coating of glass on them too, but it's very, 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 very thin. These mirror segments were then ground and polished until they were perfect, and they were shipped to the Marshall Space Flight Center for cryogenic testing. Because where the telescope is operating, it would be experiencing temperatures of about 400 degrees below 0 Fahrenheit, minus 240 Celsius. So it had to be tested to see how those beryllium segments were going to change shape. That was measured under cryogenic testing with lasers, so they knew how they were going to deflect when they got cold. They were then had a thin layer of gold applied to each of them, because gold reflects infrared radiation very well. It was vapor deposited, a thickness of about 100 billionths of a meter. So the total amount of gold on the entire telescope is valued at about $3,000. And then a thin layer of glass was then deposited on the gold to protect it. After that was applied, the mirrors went back to Marshall for another testing at cryogenic temperatures to see how well they were keeping their shape, and so they could be characterized on orbit. They then went to Goddard, where the primary structure was there. It's a composite structure, so it's lightweight. The mirrors were assembled, installed, checked out. The optical resolution of that telescope, it has a focal length of about 131 meters, has an optical resolution of about 0.1 arc seconds, which at 13 billion light years is equivalent to 6,300 light years. The sun shield comes in 5 layers. It's Kapton E with aluminum and doped silicon coatings, 5 sections. So there's some heating in between the layers, but each one gets less and less and less till you get to the actual contact with the telescope. It allowed the telescope to cool down to about 50 Kelvin, minus 370 degrees Fahrenheit, by passively radiating that heat to space. Heat was transferred to radiators to just radiate it away from the spacecraft. The near-infrared systems were working at 39 Kelvin, about minus 234 C, a little bit higher than the sun shield was able to get it, so they could radiate passively. But the mid-infrared systems went down to 7 Kelvin. So they used a helium refrigerator, a cryocooler, to bring those down to the very low temperatures they need to operate and look at the part of the spectrum that they're analyzing. This is the spacecraft folded up and stored in the fairing. It was launched on Christmas Day in 2021 by the European Space Agency on an Ariane 5 from the...
I have a question.
Yes.
How much helium was on that ship when they set it up in space?
Oh gosh. Approximately, I believe, about 150 kilograms.
150 kilograms.
Yeah, not a lot.
And so that's being depleted or evaporating or something?
Yeah, as it's cooling, it's absorbing heat, it turns to a gas, it has to be vented. Yeah.
So what was the life expectancy of that cooling system?
Depending on how well the sun shield was working, I believe it was 7 to 10 years.
That's it then?
Yeah. For the instrument that requires it. Not all of the instruments do. So that's a caveat.
So it will go on after even the helium is...
Yes, that's correct. That's correct.
One question.
Yes.
How do you predict the sun shading and
How do I predict it?
how do you predict it? Protect from micro meteorites or?
Oh,
Foreign objects.
the,
Not around.
you had, the micrometeoroid environment or orbital debris environment is worse in Earth orbit. The further you move away, the less it gets. There have been micrometeoroid strikes on Webb. There have been, but very few. So yeah, the further out you go, thank heavens you're away from the garbage that we left in Earth orbit, the garbage that we're going to be leaving on the moon. So it's less of an issue the further out you go. Did you already get it? No. Okay. Now I gotta watch you because I know you already got one. It had 50 major deployments, 178 release mechanisms had to work to deploy those 50 parts. A failure of one would have meant failure of the mission. It was the most complicated spacecraft deployment sequence ever done, and it worked flawlessly.
Cool.
And let's see if this is going to work for me. Oh, why? You opened it at home? Shoot. Okay, now it's not gonna work. Never fails. This is a video that's actually available on YouTube. It's an animation showing the deployment sequence of the telescope. This is its position. You know, the Hubble Space Telescope is in Earth orbit, about 570 kilometers up. Webb is at the Earth-Sun Lagrange point number 2, which is opposite the Earth and the Sun. It's about 1.5 million kilometers from the Earth. They like to say that it's orbiting L2. There's nothing there to orbit. It's a point where Earth, Moon, and Sun gravity create a balance point. And if you drift away from it a little, one of those is going to start pulling you, so you got to push it back a little bit. And that's what it does. So it's actually constantly going around this point because it's easier to control that way. Once it was deployed, they had to make corrections to the mirrors to get them into focus. There was sensors that measured imperfections in the alignment, and engineers took 18 images of one star with each of those segments, and using algorithms that were defined, were able to determine how those actuators on the back of the telescope needed to move those sections to bring it all into focus to create a single image. And they were incredibly successful. This is one of the first images of the Carina Nebula. It's about 7,600 light years away. It's a stellar nursery where you see all those orange glows. Those are all stars that are in the process of being born. This is a close-up of just one of those sections. I'll give you an idea of what it could do. You see this, one of those sections from Hubble on the left and Webb on the right, actually penetrating that dust to look at stars and galaxies even beyond that nebula. The star system of WASP 96b was discovered in 2014. It's about 1,150 light years from Earth. It's a very large planet that was discovered with a stellar occultation. As that planet goes in front of its star, of course the light dips. You're talking very small dip because of the distance, but that's how we detect planets orbiting other stars. And thanks to the spectroscopy, looking at that planet, it was able to find in its planet's atmosphere sodium, water, carbon monoxide, carbon dioxide, sulfur dioxide. So it's a hotter planet, but it has all the building blocks for life. This is the southern ring. It's a planetary nebula. It's a cloud of gas and dust from a star that has shed its outer layers before it dies. This is what will happen to our sun in about 4 billion years. It'll start shedding its outer layers. It'll swell to a red giant. It'll consume Mercury, Venus, and probably Earth, and it'll eventually collapse down to a small dwarf star. But this particular one's about 2,000 light years away. And again, that's a Hubble image on the left and a Webb image on the right, cutting through all that dust and gas in the infrared to look at in better detail what actually makes up that nebula.
Here's a question.
Yes, oh, I'm sorry, yes.
How big is a white dwarf star?
A white dwarf star, our sun, when it will come shrink down to a white dwarf, it'll go from 1 million miles in diameter, it'll swell to a red giant. That'll probably reach out almost to the orbit of Mars. Then it'll collapse down to a white dwarf, probably about 1,000 miles across. Incredibly dense, higher gravity. But our sun does not have enough mass to explode, it won't nova. Because again, our sun is puny compared to a lot of stars. This is a group of galaxies called Stephan's Quintet. It's about almost 300 million light years away. First discovered actually in 1877.
I'm actually working on getting a picture of that.
Ah, wonderful, excellent. And again, you look at a picture there on the right, you see Hubble, and on the left, you see the Webb telescope. So much more detail, and be able to get the infrared light coming through those dust clouds. This is gravitational lensing. Sometimes we see galaxies that aren't really where they appear to be. They look distorted because their light is being bent by the gravitational field of intervening galaxies. So again, we're seeing something where it isn't, because gravity is bending the light from them. And Hubble could identify this, but much more detail in some of the Webb images, where we can identify those galaxies responsible for the lensing. And this is the evolution of infrared spectroscopy from the WISE spacecraft to Spitzer to the Webb Space Telescope, just what we're able to do. And then we turn it on our own solar system. Here's Jupiter, looking at the auroras that are evidence in Jupiter's atmosphere, looking at the material that is shedding off of Io that actually leaves a ring of sulfur around Jupiter, and looking at the rings themselves, which are very, very dark material, but in infrared, they show up quite well. Again, here, what you're looking here is heat, infrared, translated into the visible and the spectrum. That's why the great red spot is glowing that bright color. It's hot. The TRAPPIST system, a red dwarf star, it's only about 41 light years from us, has a planetary system of 7 known planets. It was discovered from ground-based observatory in Chile in 1999, and spectroscopy has been done by Webb of each of the atmospheres of those planets. This image came out, I believe, in February. This is a galaxy that should not exist by our cosmological models. This existed only 280 million years after the Big Bang, the fully formed galaxy. So what we know ain't necessarily so. This is a nebula. I love this one. It's called the Exposed Cranium Nebula. Oh, I'm sorry, yes.
I mean, what kind of who does theoretical work to try to somehow cope with new observations?
Well, there are a lot of other astrophysicists out there now that are working, cosmologists. I don't remember the names of some of them. One is a very young woman who's about 27 years old. Stephen Hawking once said she was about 10 times brighter than he was in looking at this. I've talked to some of them, and I look at some of their math and go, no, forget it. It's just because they're not dealing in 3 dimensions. They're dealing in 4, 5, 6, 8, 9, and 11 dimensions in their mathematics. Makes my head hurt. But this is a nebula called the Exposed Cranium Nebula, and then you can see why. It looks like the brain inside somebody's head. And you can look at the detail from the near-infrared cam and the mid-infrared cams off of the Webb Space Telescope, getting the detail in that nebula. This is another planetary nebula where the material from the star has been shed off at the end of its life. And back in the neighborhood, this is Uranus. Uranus is one of the odd planets in our solar system because it's kind of on its side. It rotates the other way. Its rotational axis and its magnetic axes are way off from each other. And it's the first time it's actually been able to measure these things, looking at actually auroras in the atmosphere of Uranus. and mapping in more detail the rings, which again are blacker than coal. So visually we can't see them, but in infrared, they stand out. Now, of course, everybody asks, what does this cost? And it's a good question, it's a valid question. The spacecraft development between 2003 and 2021 was almost $9 billion. 5 years of operations, almost $900 million. The European Space Agency provided the launch vehicle and 2 of the 4 science instruments, about $750 million. And the Canadian Space Agency contributed sensors and other science instruments for about $150 million. So total cost, for including the first 5 years of operations, was about $10 billion. In that time, the US government will have spent $101 trillion. So Webb accounted for 0.0099% of all US spending in this period. The equivalent of setting aside 1/100th of a penny of every dollar to answer these fundamental questions about where our universe came from and where it's going. So personally, if you look at what we spent as a government, as represented by a dollar bill, Webb costs less than that slice of a penny. I think it's worth it. And as Carl Sagan so aptly put it, the very first spoken words he ever did in the Cosmos series, I always thought they were very simple and they were very profound. The cosmos is all that there is, or ever was, or ever will be. And every atom that's in our bodies, every atom in the material in this room was once inside a star, because all the elements of the periodic table were formed in the stars. So we are, as he put it, star stuff. So we are a way for the universe to know itself. I just pray it likes what it finds out. There's some websites here. Ron has these charts. So, however much he's going to charge you for them, you can talk to him and get a copy from him.
One parking token.
And that's really the end of my talk. If anybody has any questions. Yes, sir.
Jeff, would you be able to back out of the PowerPoint and try to run that JT deployment?
I might be able to find, if I can find it.
Do you need internet access to
No.
play it?
No.
Okay.
If I can find it. Sorry. That's just one folder,
Well, there it is.
The struggles of being a spacer. There's so much you can do.
Oh, there it is. I'm looking right at it.
Cool.
Hidden in plain sight.
There it goes.
All right.
Woo.
Yes, yes.
What is this?
Yeah, this was all happening in the days after launch. And again, the sequence was commanded from Earth, but it was all executed by the spacecraft. Because anything went wrong, there's no way to do anything about it.
How far away was that telescope from Earth? Not at all.
When the deployments happened,
Yeah.
past the orbit of the moon, well past the orbit of the moon.
So we had a time delay of what?
It would start getting worse and worse anyway, about 5-6 seconds. Probably by the time it finished was probably close to 10 seconds time delay. Yeah. Yes.
I have a couple questions.
Yeah.
Does the Hubble just rotate around the Earth
Yes.
and then the Webb is out, way out,
Mhm.
but is sort of stationary?
Yes.
Okay.
Yes. As the Earth goes around the sun, those gravitational stability points, the Lagrange points, kind of, they stay in that same position.
Okay, but the Webb is looking out into space.
Correct.
Away from the Earth.
Yes.
Okay.
And so is Hubble. So is Hubble. Yeah. Yes.
When the web unfolded, what was the force behind that? Was it springs or cables or?
Both. Both. There are usually pyrotechnic actuated restraint mechanisms that will allow a spring to start a deployment, and then there are pulleys and cables to start tensioning and pulling it. They have to move at a given rate, so obviously you don't want that cable coming off the pulley. Literally, it's the space equivalent of a Venetian blind cord, is what it comes down to. I know that sounds like an oversimplification, but honestly, it's not. First time I ever saw the sun shields that would deploy the PAM upper stage of the spacecraft from the shuttle. They were in this clamshell. That's exactly what it was. It was nylon rollers and rope. It's like they were to Kmart and bought some Venetian blinds and put the thing together. It's like
True.
But again, one thing you have to understand.
What about the future? Are they gonna have more launching?
The next telescope is the Nancy Roman Space Telescope, which is complete and should launch in the next few years. I don't have a lot of the details on it with me, but it'll be complementary to Webb. I believe it's targeted for L2, but I would have to check that. I would have to check that.
More like Jupiter's, the Greek camp and the Roman camp as well.
Oh, every planetary says, like the Earth and the Moon, there are Lagrange points. There's 5 of them, and there's one that's in the orbit of the Moon that leads it, and one behind it. They're called the Trojan points. Those are gravitationally stable points, and the things will tend to congregate there. NASA actually has a spacecraft called Lucy, which is going to one of the Lagrange points in Jupiter, because there's a whole bunch of asteroids that are there. They're gravitationally locked there. So it's going to be looking at those asteroids. Earth has it. Matter of fact, at one of those Lagrange points, there's an asteroid there now. So Earth basically has, I think for the next 20 or 25 years before it gets perturbed out of there, Earth actually has 2 moons right now, because there's an asteroid at one of those Trojan points. Yeah.
So you're saying this next telescope is going into Jupiter?
No. That was the Lucy. It's called the Lucy spacecraft.
What is it doing then?
It's going to look at an asteroid in the Trojan points.
But it's going to be in an L2 point. It's going to be stationary
At Jupiter.
At
Jupiter. It's going to an asteroid at that Lagrange point.
Is it
But the
looking at
Nancy-
Jupiter or just looking out?
It's analyzing the asteroid that's there. Yes. Yeah.
But the Nancy Roman is the one also going to L2, Earth's
Right.
L2.
Yeah, and it's a telescope. It's similar to James Webb. Again, different instruments, better classes of instruments. So again, each one is an evolution that gets us better and better imagery and more imagery, and tells us more that we've screwed up in cosmology.
So they're not necessarily getting bigger and better. They're just getting different. They're looking at different aspects.
It's kind of both.
A little bit.
It's kind of both. It's both.
Do they have a constraint on how big they can actually put in space? I mean,
Oh yeah. It all depends on what launch vehicle you're using, where you're going. It all comes down to delta V. You know, can you get there from here? You gotta make them light enough and small enough to fit in that fairing, and
The bigger the rocket, the bigger.
Until we can actually assemble something in orbit, that's always going to be our limiting.
we can't do that because we did the International Space Station. You know, you're talking something
Right.
that's 1 million pounds and the size of Brown Stadium, the old Brown Stadium. That's been in Earth orbit now for almost 30 years.
Well, I should say, yeah, build something in orbit with the purpose of
Yeah.
then boosting it
Yeah.
off to a
Or
sun
you
mission.
put observatories on the lunar near side and on the far side, so you can do 2 weeks of deep space observing from each one, and you can service them.
If you want to get much bigger, they'll probably go to interferometer.
Oh yeah.
Yeah, interferometers from the different points.
There was a study that Goddard did that actually we were a part of because they wanted to use one of the thrusters that was developed by Glenn. It was a telescope that would deploy a large diffracting sun shield in front of it, and the points of it would create a diffraction pattern, an interferometric pattern onto the telescope, and the plan was to have 3 or 4 of these. So then you could combine the images. So you had a telescope that could be almost the size of the moon to create an image. Yeah. It was never funded. There were a lot of studies done. It was called WFIRST, WFIRST. You can probably find some papers on it if you do a Google search.
The beauty of that is you get the resolution of a telescope distance between the telescopes.
Yes.
So you would be able to easily resolve planets around other stars.
Yes. We do it with radio astronomy, the Very Large Array in the southwestern United States. Yeah.
We've been there.
Yes.
Back a while ago, you showed this like graph of the universe expanding from the Big Bang.
Yeah.
Well, there was this thing called the dark age. How do we even know it existed?
We don't. It's theoretical. There's mathematics applied to what may have happened, and if you look at the Big Bang, when the universe itself was created, there would have been this flash of EM radiation, because EM radiation would have been created along with the universe. What we call the universe or space-time is EM radiation. Yeah. Where all matter is EM radiation. It's just in a different form. We're all EM radiation. Just we're bundled together. It's like one of the bad things that's taught in school is when you look at the idea of what an atom looks like. You always see these round balls and the nucleus and electrons going around. Well, that's not what an atom is. An atom is electromagnetic radiation stuck together. So what an atom is this. If you know where an electron is, you don't know how fast it's moving or where it's going. If you know how fast it's going, you don't know where it is. That's called the Heisenberg uncertainty principle. So you can know one, but not the other. So when we can put together what we observe in 3-dimensional space with what we know about the quantum universe, it's going to be this big eureka moment, and we may finally understand things.
Cool.
Maybe. Yes, sir.
James Webb is finding new, based on our current model, new galaxies that shouldn't be there.
Yes.
How far back is that point where we shouldn't be seeing galaxies? And then how much further back is James Webb finding them?
Well, again, that one image I showed, if you look at the theoretical models, starting from about less than 100 million years after the Big Bang to 400 million years of the Big Bang should have been complete darkness. And Webb has imaged galaxies, complete galaxies existing like 280 million years, right smack dab in the middle of the dark zone.
Dark Ages.
Yes. Yes.
Okay.
So
and
we know
after the Dark Ages is when we should start seeing galaxies.
Yeah. And we're seeing things that, by our models and our understanding, shouldn't exist. So our understanding is not correct.
One more question.
Yeah.
Earlier you were talking about the light spectrums.
Yeah.
And how further objects, because they're moving away, are like red shifted.
Yes.
And the closer ones are being blue shifted, right?
It depends on the object. Most objects are moving away from us. Some stars in our galaxy, like Sirius, is actually moving toward us. Sirius is actually blue shifted toward us, but most stars are red shifted from us.
Is there like at least when it comes to on a galaxy scale, is there a point where we can tell, all right, nothing else past this point is coming towards us because of the expansion of the universe? Or is it just dependent on what we're looking at?
All the observations suggest that the further we look out, the faster things are moving away from us. It's only as we get closer, like Sirius, which is about 9 light years or so from us, that has blue shift.
Anything outside the local group is moving away from us.
Yes, yeah.
So the local group is a group of galaxies that the Milky Way belongs to. There's about 100 galaxies. Anything outside that is moving away from us, but some of the galaxies within the local group are moving toward us.
Andromeda.
Andromeda,
Probably then, because we know the universe, we think we know the universe expands faster than the speed of light. That doesn't violate the speed of light rule, it's just that the entire universe is expanding faster, right?
Yeah, 'cause space is
So I would
so
think
Yeah.
there is a point then where whenever that expansion goes beyond the speed of light, you absolutely can't have anything that you would see blue shifted beyond it.
you can't see it because the light doesn't get to it.
Yeah.
Yeah, I think, I had explained once, I think this is right. We tend to think of a model that the galaxies are expanding away from us in space, but it's actually space itself that's expanding, which is pretty, it's like when you blow up a balloon, you're not, the whole thing's getting bigger.
Exactly.
It isn't that the pieces are getting bigger.
And then the question is, what's it expanding into?
No, that's philosophy.
Yeah, I think most cosmological theories have anywhere from like 8 to 11 dimensions. You know, everything in our universe is constrained to travel in the universe, which may or may not necessarily be a straight line. You know, if you look at what we classify as wormholes, Einstein-Rosen bridges, where you can traverse large distances of space, that's because you're cutting through other dimensions. You're taking a shortcut. You're going around a curvature, and by going through it, through another dimension. It's like massive objects actually bend space-time. That's Einstein's general theory of relativity. Certain aspects of Mercury's orbit can only be explained that way. So you're actually bending space-time. A spacecraft in orbit around the Earth, its clock will actually run slower than a clock on the ground because of time dilation. We're not moving at incredible speed, so it's not huge, but it is there. It can be measured.
Before my head blows up, the universe is extinct. Could we see that timeline from the Big Bang on?
Yeah.
But you're just starting to believe.
But it's going all the way out, isn't it? I mean, from the middle of the Big Bang all the way out.
Yeah.
It's not just a funnel like that. It's all the way around it.
Right. Yeah. I mean, it has to be put down on a two-dimensional graphic. But you're at a point you're moving out in all dimensions. In fact, all dimensions are being created.
So that Dark Ages thing may not be right then.
Yeah, well, if J-Wist is correct, then it's not, unless somebody's up there with a flashlight, then the theories are, sorry, they're not correct, folks.
I think that big question is, what's it expanding out into?
The more we learn, we have to learn.
The more we learn.
More questions.
The more we
Yeah.
don't know.
More questions.
Oh, thank you.
Yes.
What's causing the
You don't want it.
You get a couple more of those, you can build your own.
It's part of, again, you're looking at the Hubble constant, as the Hubble tension. How do you measure that? What does it mean? What caused it? Why is it happening? Why does the universe continue to expand? Those are fundamental questions that I don't know. I don't know that anyone does.
And how are we saying like it's expanding the distances between galaxies?
Yeah. You're seeing why science and religion can get mixed up in each other.
Jealous, more likely.
Well, I've always thought, when Galileo was essentially imprisoned, by the church, was finally exonerated by John Paul II, in the Vatican Museum, they actually have Galileo's hand preserved there. Yeah.
His what?
His hand, his right hand.
His hand?
And it's in the perfect position because it's like this.
Wow.
Yeah, I'm serious, it is. You can pull up a picture of it. That's exactly what it is. I think it's marvelous. I think it's marvelous.
When you go there, can you get a picture of that?
I will endeavor to do
Anyone
that,
else?
yes.
That sounds like, I mean, Galileo was a very crusty character.
Oh,
The,
I actually read one of his papers where others refuted what is. He's basically calling them idiots left, right, and center. It's wonderful to read. Yeah, it's great. Yeah. It was a book I picked up a number of years ago that had papers, and one of them was Galileo's in the book. It's great to read. Yeah, yeah. He was ripping them all new ones. It was great.
He wasn't a polite kind.
No. I think most brilliant people like that aren't. They don't put up with idiocy very well. You know, I always thought Benjamin Franklin had to have been a complete smart aleck. As brilliant as he was in so many areas, he had to have been.
The thing I remember Galileo, his astronomical observation work was all done quite early.
Oh yeah.
The rest of his life was all his theory, was all theoretical work.
Well, I think there are a lot of scientists that kind of lament that kind of track record too. You know, they're very brilliant in their early years, and then it's like, wonder what I can figure out next. Kind of burn their candle all at once.
Yeah. Ma'am, did you have a question?
Well, it's sort of mundane, but I just wondered, does anyone keep track of how many human beings have worked on all these things?
Oh,
you know how many hours that
yeah.
humanity has put into?
Oh, sure.
Do we?
Sure, because every project has to keep track of its workforce and how much time spent. Yeah. That's why when you look at how much things cost, like the International Space Station, like $100 billion. Oh my God, that's not $100 billion in orbit. You know, if you look at the majority of the space station is aluminum. Okay, if you took the space station and sold it for scrap metal, you get about $350,000. That's about it. All that money is down here. It's in the economy. It paid the engineers and scientists and the technicians. It paid the people cutting the grass at the NASA centers and cleaning the restrooms and fixing the lights. That's where the money is. It's all in the economy. There have been a lot of studies done on NASA funding, and the most conservatives say that for every dollar NASA spends, $7 is returned to the economy because of spin-offs, because of other industries. So there's no other federal agency that can say that. There's none. Yes?
Is that the simple reason why it's made in so many different places and parts? And
No, that's politics.
That's
politics. That's politics.
That's the lowest.
Unfortunately. Yeah, NASA has 10 field centers.
Well, it seems like it puts it at risk with just the shipping.
Oh, it does. Absolutely, yeah. And everything, most people don't realize, the Orion spacecraft went through all of its testing to determine that it could fly and carry human beings in Sandusky at the Armstrong Test Facility. Because that's the only facility in the world where you can do all the environmental testing necessary to qualify a spacecraft for flight under one roof. Otherwise, you got to send it to different buildings or across the country to different facilities. It's the only place in the world where it can all be done in one roof, right in Sandusky.
Excuse me, is that the old Plum Brook station?
Yes.
Is that still in existence?
Yes. Yeah.
Fire.
All of SpaceX's spacecraft, all of Sierra Nevada's, the Dragon, the Dream Chaser, Northrop Grumman's, Cygnus, all of them, they've all been tested out here.
Okay.
Payload fairings for every launch vehicle have been tested out here, including Europeans. They bring them across and bring them out to our facility. It's the only facility in the world where you can do it.
Back in my bowling team's an engineer who grew up in Sandusky, and they used to hike all around.
Yeah. It's only a few facilities on 6,500 acres, but it was designed for hazardous testing. The facility where Orion tests was actually built to test nuclear spacecraft. Never saw any, of course.
So NERSA or DEVA?
Yeah, the NERVA program. Yeah, NERVA was a nuclear thermal propulsion system. It was they completed testing the flight system that was capable of sending humans to Mars and back again when the program was canceled in 1972.
Oh.
We've been trying to recapture it ever since.
Gotta bring that back.
Yeah. Yes.
I recall reading about a near future telescope that was going to be able to let us see if there were things coming at us from the other side of the sun, like asteroids or something. Does that sound familiar
NASA has a planetary defense program, which is linked to telescopes around the world looking for asteroids and such. But, we're constrained as to how small objects we can see. There was an asteroid, I don't know if it's already passed the Earth or it's about to, it'd be between the Earth and the Moon. It was only discovered a few hours before the passage. The Chelyabinsk meteorite that exploded in 2013 was never detected.
But that same day, they were looking for another asteroid.
Yes, they were.
From the moon.
Yeah, you're right.
And all of a sudden, this one hits in Russia. It's like,
Yes.
wow, we got that one off.
What about the one in Medina?
Yeah, that was very small. That one was really interesting too because it was on a north-south trajectory, which is very strange. There's certain asteroids that are fragments that are like between the Earth and the Sun that have danger for Earth. They're called the Apollos. But actually, fragments of that were recovered by meteorite hunters. I was actually at an astronomy forum in New York in April, and they actually had pieces of it for sale. If you wanted to spend $3,000 for a little slice about this big, Exactly. Exactly. Yeah.
So, James Webb has like a lifetime of 7 years, you were saying?
Then again, depends on how quickly it goes through that liquid helium, how much, you can reduce how much you're using the instrument.
So what's the plan like once it says like it's done? How are we still going to keep observing that?
Well, again, it's only that instrument that would have to be shut down because it couldn't be kept cold enough. All the other instruments would still operate. But eventually, like Hubble, there's going to be failures. The attitude control system will run out of its propellant. Now, one of the deployments you saw was called a momentum flap. It's basically a large, flat, very thin piece of mylar covered framework. It uses solar pressure to actually do attitude control. So it supplements the wheels, the momentum wheels that are on there, and the thrusters. The thrusters are always the last resort because those are consumables. Hubble doesn't even have thrusters. Hubble doesn't have any propulsion attitude control capability at all, other than its reaction wheels to move it for pointing and keep it stable. And 2 of the 3 of those have failed. So it's on its last legs. But it's been operating since 1990.
Right, to be fair, it was only going to last X number of months, right?
Yeah.
And it's been up there 30 years.
Yeah. Look at Voyager 1 and Voyager 2.
Yeah.
They were supposed to run a few years. It's almost 50 years later. We're still in contact with them.
Does Hubble generate any revenue? Do they sell time? For that use?
NASA, as a government agency, is funded by taxpayers. So time is scheduled, but there are no charges for that time. The funding is it's all taxpayer funded. It's all taxpayer funded. If you look at NASA's yearly budget and you represented the portion of the federal budget that it represents, it's about 0.36%. So it's 1/3 of a penny of every dollar. If you took the population of the U.S. and you got a bill in the mail to fund NASA, the bill would be about $75 for a year. If you got a bill to fund the rest of the government for a year, it would be $17,000. So
That's worth it.
I'd like to see the Department of Defense, not the Department of War, because that's an illegal name. Could get by with a few less cases of paper clips, you could double NASA's budget. And one of the handouts I have on the table back there actually talks about that. So you folks are all welcome to the handouts back there. I know I don't have enough, but if anybody, I can bring some more. I'll be coming out to your picnic on the 30th. I can bring some more. Ron just lets me know how many we might need. I can bring more of everything. So
So save your questions for the picnic.